The story of spaceflight is the story of energy. Energy lifts a space vehicle from the Earth, propelling it into space. Energy then directs the movements of the spacecraft in space, changing its flight path by increasing or decreasing its speed, and controlling its attitude by forcing it to yaw left or right, to pitch up or down, to roll, and also to move sideways. And energy provides the electric power on board a spacecraft. Power needed for so many vital functions, from operating instruments and pilot displays to transmitting radio communications to Earth. The first stage of the Apollo Saturn V launch vehicle is a formidable example of energy harnessed by man, then released on his command. Its 5 engines generate 7.5 million pounds of thrust to propel the Apollo space vehicle through the first phase of a manned lunar mission. But this brief film chapter in the story of energy and spaceflight begins after the stages of the launch vehicle have performed their tasks. Our film concerns energy as it is applied on and within the spacecraft itself. The propulsive devices which enable it to change velocity and maneuver in outer space. And the electric power needed for its operations as it travels through outer space alone. Finding and selecting the types of energy best suited for manned spacecraft propulsion and power is the responsibility of the Propulsion and Power Division of the Engineering and Development Directorate of NASA's Manned Spacecraft Center at Houston, Texas. Here, scientists, engineers, and technicians study and apply the principles of energy, determine spacecraft requirements, and design and develop systems, subsystems, and components of propulsion and power. Primarily, they monitor the design, development, and manufacture of such units by private contractors throughout the United States, and subject developmental hardware to exhaustive tests to verify its performance and reliability. From abstract theory to final developmental testing, the Manned Spacecraft Center specialists in propulsion and power bring to their work a thorough knowledge of the state-of-the-art and the ingenuity needed to unlock new applications of energy. Analyzing the energy characteristics and capabilities of various systems is part of their daily work. Designers are bound by many constraints in deciding which sources of energy and which energy conversion devices to select. Available funds and the target date for a mission are design determinants, since only those systems can be considered which can be developed, thoroughly tested, and produced by the required date. The weight of the payload which can be placed in space is limited by the capability of the launch vehicle. Each system and subsystem must meet the tests of safety and reliability demanded for manned missions. The special requirements of a particular mission for both propulsion and power must be identified, then analyzed. Considering propulsion first, there are 2 categories of spacecraft systems, primary and auxiliary. Primary propulsion systems are used for large increases or decreases in spacecraft velocity. Auxiliary propulsion systems are attitude control systems. Some can also achieve small velocity changes, but their main function is to orient the spacecraft in pitch, roll, and yaw. Let us identify some of these systems by comparing our first three manned spacecraft: Mercury, Gemini, and Apollo. Comparatively, the propulsive energy requirements of the Mercury spacecraft were not large. Only one primary propulsion system was needed: the retro rockets fired to reduce velocity for deorbit and re-entry into the Earth's atmosphere. There was also an attitude control system and a launch escape system. For Gemini, the next spacecraft to evolve, propulsive energy requirements were greater. In addition to a seat ejection escape system, an attitude control system, and retro rockets for deorbit, Gemini needed an additional propulsion system to change the velocity of the spacecraft for orbital changes and rendezvous maneuvers. In the case of the three-module Apollo spacecraft, energy requirements are immense. In addition to a more powerful launch escape system, large amounts of propellant and three primary engines are needed. The service module has a main engine to correct the flight path on the way to and from the moon, to reduce speed to enter lunar orbit, and to thrust the spacecraft out of lunar orbit into a return flight path. The Lunar Excursion Module, called the LEM, has a descent engine to land on the moon and an ascent engine to lift off from the moon's surface. In addition, three auxiliary propulsion systems are needed, one on each module for attitude control. Altogether, 44 rocket engines are required for the three auxiliary systems. To better understand the tasks of a propulsion engineer, let us now analyze certain Apollo spacecraft propulsion requirements by reviewing part of an Apollo manned lunar landing mission profile. After the three modules of the spacecraft have been launched into Earth orbit and then into a trans-lunar flight path, with the LEM still attached to the third stage launch vehicle, the adapter shielding the LEM is opened by a pyrotechnic subsystem. The rocket engines of the service module's auxiliary attitude control system then maneuver the command and service modules so that they pull ahead, turn around, and return to dock with the LEM. The service module's main engine is now in the clear for firing. The spacecraft is then separated from the third stage launch vehicle. Sometime later, the crew prepares for the first of three mid-course corrections which may have to be made in the flight path on the way to the moon. Attitude control engines orient the spacecraft precisely so that the force vector of the main engine is aimed in the required direction. The main engine is then fired for the first time. This is the first use of the tremendous energy of this primary propulsion system to change the velocity or direction of travel of the spacecraft. Between mid-course corrections, the spacecraft coasts, with the attitude control engines stabilizing the spacecraft for navigational sightings or scientific measurements and controlling its roll at the rate of 1 or 2 revolutions per hour to distribute the sun's heat evenly. After the final mid-course correction, the spacecraft approaches the moon, but its velocity and flight path, if undisturbed, would carry it past the target. So the main engine is again fired, this time for approximately 6 minutes, during which the combustion energy of the propellants reduces the inertial energy of the onrushing spacecraft, thereby reducing its velocity to a nominal 3,600 miles per hour. At this point, the spacecraft's flight speed and the moon's gravitational pull are so balanced that the spacecraft falls into a nearly circular orbital path around the moon. The two lunar explorers transfer from the command module to the LEM, and the LEM is separated from the command and service modules which will remain in circular orbit carrying the third crewman. Orbital velocity would also keep the LEM flying in this circular path around the moon if no new force were applied. This new force is obtained by firing the LEM's descent engine. Its retrothrust reduces the LEM's velocity so that it enters a separate descent orbit. When the LEM reaches the point in its descent orbit closest to the moon, its descent engine is again ignited for a continuous burn to further reduce its speed and perform the landing maneuver. A large amount of propellant must be expended to overcome the inertial energy of the LEM. To bring it to rest on the moon's surface, several other features are also essential. The attitude control system must properly stabilize and orient the spacecraft. The descent engine must be gimbaled so that the direction of its thrust can be precisely aimed. And the engine must be throttleable so that the pilot can apply variable amounts of thrust. These features enable the pilot to guide the LEM along a carefully planned flight path, to let it hover over the landing site, and, if necessary, to change its course before touchdown. The next propulsion requirement of the mission is the launch from the lunar surface back into lunar orbit. The empty descent stage serves as a launch platform for the ascent stage. A large amount of propellant and a launch engine must be carried to the moon to supply the energy required to return to lunar orbit. The attitude control system aims the thrust of the ascent engine. The ascent maneuver brings the LEM into lunar orbit about 5 miles from the orbiting command and service modules. The LEM's attitude control engines are then used to complete rendezvous. After the two explorers have rejoined their fellow crewman in the command module, the LEM is separated to remain in lunar orbit. Oriented by the service module's attitude control system, the powerful main engine is then fired to give the command and service modules the velocity to leave lunar orbit and enter a flight path back toward Earth. Mid-course corrections may again be made by firings of the main engine. About 20 minutes before re-entry into Earth's atmosphere, the service module is jettisoned. The command module falls toward Earth, reaching a speed of 25,000 miles per hour as it enters the atmosphere. A heavy and complex retro-rocket propulsion system is not needed to slow the spacecraft to below orbital speed in return from lunar missions. Instead, the flight path is precisely aimed at a narrow re-entry corridor, which brings the spacecraft into the atmosphere, where the tremendous kinetic energy of the spacecraft can be dissipated by atmospheric drag braking. The mission's final application of propulsive energy is the use of the command module's attitude control engines during re-entry. The attitude control system orients the spacecraft and rolls it to control the direction of its lift vector. This makes possible guidance of the spacecraft through the corridor in the atmosphere to the desired point of parachute deployment. After analyzing the primary and auxiliary propulsion requirements for a spacecraft to carry out its mission, spacecraft engineers must select and develop a full complement of propulsion systems widely differing in specifications so as to meet widely differing mission requirements. But the principles of rocket thrust are the same for all engines, large or small. The propellants are injected into a combustion chamber where they ignite and burn. In the combustion process, the inherent chemical energy of the propellants is transformed to a directly usable energy form. The thermal energy of the extremely hot combustion gases, which reach temperatures of 5,000 degrees Fahrenheit and higher. The purpose of the combustion is to produce pressure within the combustion chamber, because it is the pressure which produces the propulsive force, or thrust. The pressure within the combustion chamber acts equally on all surfaces. Thus, the pressure force acting to the left is exactly counterbalanced by an opposing pressure force acting to the right. In a similar manner, if the combustion chamber were completely closed, the pressure force acting upward would also be exactly counterbalanced by the pressure force acting downward. In this case, all pressure forces would be exactly balanced and there would be no net force or thrust. In order to produce thrust, then, an opening called a throat is made in the combustion chamber through which the hot combustion gases are exhausted. Now the pressure forces are no longer balanced. The pressure in the upward direction is acting against a larger area than the pressure in the downward direction, since some of the lower surface was removed to form the throat. A net thrust propelling the rocket forward is the result. Additional thrust is obtained by the use of a rocket nozzle. Again, the pressure forces acting to the sides exactly counterbalance one another. But since the nozzle has no rear surface, the upward and downward acting pressures are again unbalanced, resulting in additional thrust on the rocket. Since the hot combustion gases are continually being exhausted from the rocket through the throat, a continuous supply of propellant must be burned to maintain the desired pressure in the combustion chamber. Although basic principles of rocket thrust are the same in all propulsion systems, selecting the best systems to meet mission requirements is not easy. There are many propellant combinations, pressurization systems, propellant tanks and tank arrangements, engine systems, and system operating parameters from which to choose. The ideal system would give the highest performance, have the highest reliability, and weigh less than any other system. But it is difficult to achieve these three factors simultaneously. Some trade-offs must be made. For manned spacecraft, the prime factor is high reliability. Careful analyses and vigorous discussion by preliminary design engineers precede the selection of propellants and propulsion systems, which account for the largest portion of spacecraft weight, 73%, for instance, of the weight of the Apollo spacecraft. Chemical propellants in use today can be classified broadly as liquids and solids. Current missions generally rely on liquid bipropellants consisting of a fuel and an oxidizer. Liquids offer greater flexibility in packaging and are more suitable for engine restarts and throttling. For example, the Apollo service module main engine must ignite, burn for a few minutes, shut down, and reignite several times on a mission, while the engines of attitude control systems must be able to fire in pulses lasting only a few milliseconds and do this thousands of times during a mission. In slow motion inside this transparent test chamber can be seen another feature of most liquid bipropellants. They are hypergolic, that is, they ignite on contact with each other. This eliminates the need for a complex ignition system. This injector test shows how hypergolic propellants are injected under pressure into a combustion chamber. Using water to simulate both oxidizer and fuel, the injector spray action can be seen, injecting the oxidizer at an angle from the inside channel outward into the chamber, then injecting the fuel from the outer channel inward into the chamber. In actual combustion, the oxidizer and fuel are injected at about the same time. The two vaporized chemicals mix, ignite, and burn to produce the high-pressure gases in the chamber to give thrust. From injection of propellants to ejection of combustion gases takes 3 or 4 milliseconds. That is 3 or 4 one-thousandths of a second. Spacecraft retro-rockets for deorbit and escape system rockets typically utilize solid propellants. Here, the launch escape system of Apollo is being prepared for a flight test at NASA's White Sands Test Facility in New Mexico. Instant readiness to produce high thrust in a short period is one of the advantages of solid propellants. Others are storability and inherent simplicity. There are no moving parts, such as valves in solid propellant rockets. The propellant is packed within the combustion chamber in a predetermined shape. This is called the grain, and it is ignited by a pyrotechnic igniter. The shape of the grain determines its burn characteristics. Pyrotechnic igniters are packages of solid propellants activated by either an electric or mechanical impulse. The heat and gas produced ignite the rocket grain. But pyrotechnic devices of other kinds are used for purposes other than solid propellant ignition on a spacecraft. Their explosive force is used to separate stages, to cut the lines of parachutes after they have served their purpose during re-entry, to open the LEM adapter before separation of the spacecraft from the launch vehicle, and for other tasks. On the Apollo spacecraft alone, there are more than 100 pyrotechnic devices, all the responsibility of the Propulsion and Power Division at the Manned Spacecraft Center. From spacecraft propulsion and pyrotechnics, let us now proceed to a different but equally vital use of energy, spacecraft electric power. Every instrument in the cabin of a spacecraft is operated by electric power stored in batteries or generated by onboard systems. For short missions, storage batteries are adequate to supply power. The Mercury spacecraft relied on them entirely without a single failure. But storage batteries cannot be recharged when they are the sole source of. To store enough energy to meet the requirements of extended missions, such a storage battery would be far heavier than systems that can generate and supply power on board the spacecraft as it is needed for the mission. Therefore, Energy Systems engineers investigate several different power supply sources for long missions. For example, fuel cells, solar cells, and nuclear systems, which are even being developed to supply power for instruments left on the moon to transmit data to Earth. The 8-day mission of Gemini 5 was the first use of fuel cells in space to supply electricity. The Gemini fuel cell works like this. Oxygen and hydrogen are carried in tanks in their cryogenic, extremely low temperature state. Heat is applied to the two fluids which enter separate compartments in the fuel cell. The compartments are separated by a plastic membrane, an organic polymer with a molecular structure having the properties of an electrolyte. The membrane itself is sandwiched between two porous catalytic electrodes. Oxygen is pressurized into the compartment next to the positive electrode, hydrogen into the compartment next to the negative electrode. The electrons separate from the hydrogen atoms and travel along an external circuit toward the positive electrode. Now, this creates electric power. The hydrogen ions, that is, the nuclei of the hydrogen atoms which have lost their electrons, migrate through the electrolytic membrane and combine with the oxygen to form H2O. On extended missions, this water may be collected in tanks for drinking and other onboard purposes. Two independent systems composed of several cells are carried on Gemini missions. Each system has a maximum output of about 1,000 watts. As in the case of rocket engines, fuel cell principles are the same, although there may be several different types of systems, depending on mission requirements. This is a test model of the fuel cell system for the Apollo spacecraft. The Apollo cell utilizes a liquid electrolyte instead of an electrolytic membrane for ion exchange. Still another concept being studied is a fuel cell with a different type of electrolytic membrane consisting of asbestos saturated with the liquid electrolyte. Experimental models of this type have been used to drive tractors and other machines. More advanced engineering models of this capillary membrane fuel cell are being developed by NASA for future manned spaceflight applications. Another source of electric power is the solar cell, which has been widely used on unmanned space missions. Solar cells may be adapted by power engineers for use on manned missions. Here, a solar simulator radiating light energy called photon energy, comparable to that of the sun's rays, is being beamed onto a solar cell array in an environmental test chamber, simulating the vacuum of outer space. In another area of the Advanced Power Systems Lab, a second subsystem for a possible solar cell power system is being given a test to determine its maximum life. This is a secondary storage battery which can be recharged many times. Since a spacecraft using solar cells may be in the dark, behind the moon or a planet, during part of its mission, these dark phases. In addition to use of the sun's photon energy to activate solar cells and produce electric power, radioisotopes and nuclear reactors may be used as sources of heat energy for two other types of power systems called thermoelectric and thermionic. Thermoelectric conversion of heat to electric power is accomplished by applying heat to two different materials connected together. When heat is applied, the temperature gradient across both materials concentrates the charge carriers. This sets up a difference in the electric potentials of the materials. Electrons from the negative material flow in the external circuit toward the positive material, thus creating usable electric power. Radioactive isotopes are of particular value in thermionic systems. Experimental work on SNAP-13 radioisotope thermionic generators is carried on in the Advanced Power Systems Laboratory. Thermionic systems provide electric power in a manner similar to that of a vacuum tube by utilizing the electrons boiled off from a heated surface and collected by a cooler surface. Power systems described so far have been static systems, systems which provide for the direct conversion of energy of various kinds into usable electrical energy. Another category of systems under study for spacecraft are dynamic. They utilize an indirect method of converting energy to power. One type is similar in principle to a diesel engine, except that its energy source is the internal combustion of hypergolic propellants. These ignite, burn, and drive a reciprocating piston, which drives a generator to produce electric power. Another type of dynamic engine under study works on the same principle as turbine generator plants on Earth. A heat source, such as propellant combustion, can be used to convert a working fluid into a vapor, such as steam. The steam causes a turbine to rotate, and the turbine drives a generator. At the 120-acre thermochemical test area at the Manned Spacecraft Center, all of the various energy systems of electric power, as well as pyrotechnic devices and systems for spacecraft auxiliary propulsion, are studied in developmental stages and given additional tests. In this area, captive firings are conducted to determine engine performance characteristics, which are carefully monitored and recorded during test firings. Here, too, a variety of tests are conducted on power supply systems, such as fuel cells in space environment chambers, to determine their operational characteristics and maximum life. Of the thermochemical test branch, like those of the entire propulsion and power division at the Manned Spacecraft Center, are contributing each day toward our nation's mastery of the complex technology of spaceflight. It is a continuing process with constantly improving systems and techniques. The story of spacecraft energy for propulsion, pyrotechnics, and power is therefore a story whose final chapter, as yet, can only be imagined.